which is the acid-base equilibrium. First thing we're going to talk about is acids. The oldest definition of an acid is the Arrhenius definition, and according to that, it is a proton or an H plus donor, and a base is an OH minus donor. Well, this is an old definition. It doesn't really work. The only reason I mention it is because for some bizarre reason, it shows up on a lot of standardized tests. And I'm not really sure why. The definition we're going to use is the Bronsted-Lowry. And according to it, an acid is a proton donor. Now, usually in the form of H3O plus, and a base is a proton acceptor. This definition is a little broader because things like ammonia in H3 we know is a base, but it can't donate a hydroxide, but it can accept a proton. The other thing is this broadens the definition because this will then include the deuterium isotope, etc. Now the third definition, which we used when we talked about complex, is Lewis definition. A Lewis acid is an electron pair acceptor. And if you think about it, Lewis of Lewis structure fame was dealing with electrons, so a base is an electron pair donor. So Lewis definition is the broadest. So all Bronsted-Lowry acids will be Lewis acids, but not all Lewis acids will be Bronsted-Lowry acids. Same thing with the bases. Some terms associated with acids and bases. The H3O plus is the most common form. This is the hydronium ion. This is what carries the proton. This is actually not a true structure. It actually takes 4 waters, not 1. So the true structure is H9O4 plus, but nobody really wants to write that. And the other thing is you'll see usage of just the proton because it can exist that way, but it's easier bookkeeping method. This is the base form. This is the hydroxide. HCl is a monoprotic acid, and it's a monoprotic acid because it only contains 1. Sulfuric acid is a diprotic because it contains 2 protons, and H3PO4 is triprotic. Anything more than 1 can be considered a polyprotic acid, and we're good to go. Now, if we have something, and I'm making up an acid here, I don't know if this one's actually real or not. Okay, this would be the acidic protons. These would be structural, so you can't lose the structural protons, you can only lose the ones out front. All right, so what's a strong acid and what's not? Well, the easiest thing to do is for you to memorize this list. And if you look at it, chlorine, bromine, and iodine are in the same family. And then sulfuric acid, first proton only, nitric, chloric, and perchloric. So there are only 7 of the strong acids. On the base side, group 1 and group 2 hydroxides. Not all of the group 2 hydroxides, magnesium isn't. O2 minus, if you take O2 minus plus water, you end up producing 2 OH minuses. So you pick up a proton from 1 water, and that leaves you a hydroxide there. Hydrides are actually very strong bases, and what they tend to do is pick up a proton and produce hydrogen gas and OH minus. So the trick is if it's on the list, it's strong. If it's not on the list, it's weak. So the easiest thing is to know the list because your definition is it's not on the list. All right, let's talk strong acids and weak acids and what they look like. What is a strong acid? Well, a strong acid will dissociate completely. And you know this because it has a one-way arrow. It's one way, see? So this is your acid form. This is your base form. This is a strong acid. It's a proton donor. And when we go back down here, this is a weak acid. You know this is a weak acid because it's an equilibrium. That means this will be a Ka, and this is your acid form, and this is your base form. This is kind of like redox when we talked about it before. You can't have one without the other. If something acts as an acid, something else has to act as a base. So for just a generic weak acid, this is the acid form. This would be the base. You know it's a weak because it's got here. A is for acid, so if you notice it's donating a proton as it goes. So that's what the acid forms look like. Now remember the bases, they're again going to dissociate completely. But in this case, when they dissociate, they just become aqueous. They don't act, this is the base form. They're really, in this case, I just said you have to have an acid with it. Well, that's true, but, excuse me, this is the one time you just get a hydroxide. It usually reacts, etc. Now, again, the weak system, this is the base form. In this case, we have to have our acid form. So we know that this is weak, so it is a Kb. If a Ka is a weak acid, a base is a Kb. This is the generic form, just like Ha was for acid because it donates a proton. B is for base, and it picks up a proton. So this water will serve as the acid form as it goes. So basically the bottom line with these is that you have strong versus weak, and how do you tell the difference? Strong is one way arrow, weak is an equilibrium, or it's on the list. So that brings us to acid-base conjugate pairs. Yes, let's call them conjugate pairs. No, they're conjugate pairs. So a conjugate base is what you get or what results when something loses a proton. Okay, well, which makes sense. That means it acted like an acid. So once it lost that proton, it no longer has it. It's going to possibly want it back, which makes it a base. And we talk about acid-base pairs as being neutral, and conjugates tend to be not always, and not always on the neutral. They tend to be charged. So the conjugate acid is what results when something acts as a base. So if it's going to act as a base, it's going to gain a proton. So it acted as a base. So basically, the trick to acid-base chemistry is to figure out who's got the proton, where's it going, have you gained it, are you losing it, what are you doing, okay? So back to our strong acid, when we have our acid and it dissociates, then this would be the conjugate base of the acid. This is my weak acid. This is my weak base. So this would be the conjugate acid to the base. These pair and these pair. So this would be the conjugate base. And it's real easy to look at it because you know it's a base because it doesn't have any protons, whereas the conjugate acid has an extra proton. So again, we have an acid, we have a base. This one pairs with this one, so this is the conjugate base, because this is what results after it's given up its proton. This one acts as a base, so now this is the conjugate acid. Same thing with the bases. Here's our strong base. This would be the conjugate acid of the strong base. Down here we have a weak base. And again, you're looking for the pair. So it'd be this one. This one has a extra proton and a positive charge, so it's the conjugate acid. These two pair. This is the acid form, so this is the conjugate base. And you're like, wait, but that was the base form. Yep. So again, weak base, acid, weak acid, conjugate acid, conjugate base. Notice they pair. All right, so if we're trying to identify a molecule or an ion as an acid or a base, and then we're supposed to identify as strong or weak. So first off, we look at this. Does it have a proton? Yes. So it's going to be an acid. Now, you should recognize that's on the list, so it's a strong acid. This, however, has no proton, but it has a negative charge, so this is going to be a base. All right? And it's not anywhere on the list, so it's going to be a weak base. This is HNO2, so it's an acid because it's got this proton to donate. But it's NO2, so this is nitrous, not nitric, so this is a weak acid. Notice that nitrogens are bases unless combined with oxygen. So this nitrogen is combined with oxygen, so therefore it's acidic. This one has no oxygen, so this is a base. What kind of base is it? It's a weak base. Okay? So it's real simple. Let's complete the equations we see here. And all we're doing is playing who's got the proton. So if you notice, this one has a proton to donate. So it's going to donate it to the acid. This will be the acid, so therefore this one is the base. Plus what's left, which is C and minus. So if you'll notice, this will be the conjugate base. This is the conjugate acid. Okay. HBr, both of these happen to be strong. So this is actually easier if you write it as HOH. Because here's your H, and here's your OH. We know this is water, plus KBr. So remember, this is a neutralization reaction because here's your salt, and there's water. So this is the acid. This is the base. This is the conjugate acid here, and this would be the conjugate base. Okay, this is an acid. We know this because that's the acidic proton. This has got nitrogen in it, so it's going to be the base, which means it's going to pick up the proton. Typically, you put the proton on the end with the nitrogen. So this would then be the conjugate acid because now it has an extra proton and a charge. That means this is C2H3O2. This is acetate ion, so this would be the conjugate base. So notice we're working with acids and conjugate bases, and it's just a matter of identifying. Now this is kind of a fun chart because this makes you really think about who's got the proton and where it goes. So remember, an acid is a proton donor. So the conjugate base is what you get after the proton has left. So if this is an acid, it's going to donate a proton, so we're going to get HPO4 2 minus. Notice that when we lose the proton, we're going to lose an H plus, which means we're going to gain a negative 1. All right, so in this one, this is the conjugate base, so we've already lost our proton, so let's put it back. And so we'll end up with H2, because when we put it back, we're going to add H plus back. So this one's going to donate a proton, So we'll have SO3 2 minus. This one's going to donate a proton, so we got F minus. Now on the other side, and I'm going to change colors just so we differentiate, this is a proton acceptor. And the conjugate acid is after it has accepted it. So what you have here is, if this is the conjugate acid, so we've already accepted a proton, give it back. So we end up with PO4 3 minus. Now if this is going to accept an acid, then we get H3O plus. This one we get HClO2. And this one's already gained the proton, so we've got to give it back. And again, we want to give the one back that's attached to the nitrogen, not the carbon. So this is actually a really, really good problem, because if you can do this, this will tell you whether or not you understand the game of who's got the proton. And acid-base chemistry tends to drive people a little on the crazy side. And it's because it's actually really, really simple. It's not the big things that get you, it's the little easy things. It's one of those things that once you get it, you whack yourself in the head and go, I can't believe I couldn't get that. But once you got it, you got it. But until then, it's really frustrating. So here we go. Water can act as both an acid and a base. When it acts as a base, it gains the proton. So here's your conjugate acid. So it's paired. That would be your conjugate base for the acid. So here it's going to act as an acid. So this is the conjugate base. No, that didn't make any sense. That's not it. This is the conjugate base. Y'all let me get away with that. All right, and I fell for the oldest trick in the book, being tired. No, this is the conjugate base. And this one goes with this one because it's got the B. Now, it's amphiperiodic or amphoteric, which means it can act as both an acid and a base. And this is easy to remember. I don't know why they have two terms, amphiperiodic and amphoteric, but think about what an amphibian is. It spends half its life on water and half its life on land. So in the acid-base world, you spend half your time as an acid and half your time as a base. Now, water is not the only one acts as both. Water's not the only one that'll do it. Carbonic acid, this is actually the one they use to figure out your level of oxygenation in your blood. Is CO2 acts as your buffer. More about that in the next chapter. So what we have here is this is acting as the acid because it's donating a proton. So this would be the conjugate base. Here it's acting as the base because it's picking up a proton, so this is the conjugate acid. So again, this is the blood gas buffer reaction that is used in respiratory therapy, etc. Now, again, these are not the only ones. There are a lot of them that can do this. Here's another example of one. This one says write the equation acting as an acid, well, as a base in water. Let's go ahead and have it act as both. So we'll do the acid first. HSO4 minus goes to H plus SO4, 2 minus. Okay, remember, H plus is the same thing as H3O plus for those of us who hate writing extra things. Okay, so when it acts as the base, it's going to pick up a proton. And notice when it acts as a base, you have to have water present to gain the proton. So you have H2SO4 plus OH minus. Okay, so the question is HSO4 minus amphiprotic? So, yes or no? Okay, no. Wait, what? But you do that. Yep. This is a no-go because if you notice this, and I don't know what that stray line is doing around there, but if you look at this species here, this is a strong acid. Remember, the definition of a strong acid is it dissociates completely, which means it will not go back to form it. So this half reaction can't go because it cannot form a strong acid back. So the answer is no. I mean, that was a trick question. I tend to not do that to you on exams on the grounds that usually it's a much better or needs more information. And on tests, I try to keep it clear. I know y'all don't think so on D2L, but truly I try.